I think when anybody gets cancer, you probably think the worst.
The attitude about cancer in those early days was one of complete secrecy, fear, and disgust.
But the fact is that we didn't mention the word. We didn't talk about cancer.
When you are told you have melanoma, then it's just, terror, because it's deadly and it goes very fast.
Everybody's cancer is different from everybody else's cancer.
I just want to be around with my family, my husband.
Cancer at the present time, globally, is a public health emergency.
"50 years ago, no one even dared say the word cancer. It was considered a death sentence. Treatments were brutal and largely futile. Cancer was considered an impenetrable black box. It was believed that it had a single cause and that one day there would be a single cure, which would spell the end of this lethal assassin. This enemy within currently kills at least 8 million people across the globe each year and devastates the lives of millions more. The battle against cancer over the last 5 decades has been an epic struggle involving doctors, nurses, researchers, politicians, and above all, patients. The story of cancer is an incredible one. What follows shows just how far we've come in piecing together the puzzle that is cancer, understanding, diagnosing, treating this enemy within us. We begin in America, in a small town in Maine, with someone with a place in cancer history. In 1964, Karen was diagnosed with leukemia. Then, just 13, she was lucky because she lived close to Boston, where a new regime of drugs was being trialled in children with leukemia. It was called VAMP and involved huge doses of 4 different highly toxic drugs. It was a brutal experience, which Karen can relive as if it were yesterday.
Everything hurt. My arms, my legs, my stomach. And I would be in a fetal position for a long time. And it got to the point where I couldn't walk because my legs had bent. I was hooked on morphine for a long time, too. I would scream in the middle of the night, "Nurse, nurse," because I needed that morphine shot. It's just a totally different world, a twilight world. You're just existing. A little boy across the hall from me, he died of leukemia. And it was sad because I asked the nurse where he was, and she said that he had passed the night before.
The irony was that Karen never even knew she had leukemia, not until years afterwards. Nor was she aware that most of the children who had those early combination therapies, after a few flickering months of remission, died. Most of all, she never could have realised that her survival was the start of a revolution in leukemia care, which started here in Boston, led by legendary cancer doctor Sidney Farber.
Dr. Farber, I think, was one of the most fascinating men I ever saw. First of all, he was totally brilliant. I mean, he truly had an elephantine knowledge of pediatric hematology and oncology. He was a man of very fixed ideas, however. His theory was that he could kill a number of the cells with a single agent, and then when resistance emerged, he could kill them again with a second agent. That was his whole approach. That turned out not to be correct, that the only way to really master resistance is to treat with several drugs with different actions all simultaneously. But as we were learning how to do that and learning the doses and schedules, there was terrible toxicity. Believe me, I know. I was there in the very beginning of it. And it was dreadful. I saw about 50 children with leukemia when I was at the National Cancer Institute in the 50s using just 2 agents. And I didn't save a single one, and I made every single one of them terribly sick.
It led to a clash of wills. Farber, desperate not to make his children any sicker than they were already, wanted to give the drugs one at a time, while paediatricians like David Nathan insisted it had to be all 4 at once. In the end, ironically, Karen survived because she wasn't treated by Farber himself. She had all her drugs simultaneously. Farber later came round to this approach and became the great champion of combination chemotherapy. In the 50 years since Karen's mother was told her daughter had leukemia, hundreds of thousands of parents have been given that same awful diagnosis. And no matter where you are in the world, rich or poor, cancer still has the same power to shock, as it did for Holly and her husband Ola here in Sweden. Holly took her daughter Kate, listless and tired, to the doctor. When the doctor called them later that day, the news would change their lives forever.
And that's when the floor fell out from underneath us. I think when anybody gets cancer, you probably think the worst. I think that's just kind of an automatic reflex that you do that.
Their reaction is typical. Childhood leukemias are perhaps the cruelest of cancers. Fast and vicious, they snatch previously healthy children within months. Treatments today are founded on those flickers of remission seen 50 years ago. And while developments in the prevention of nausea and infection have had significant impacts on their effectiveness, the treatments remain brutal.
She was losing weight, she was losing her energy, she was just this body laying on a bed. There wasn't anything to her, really.
Couldn't get any response. You tried to get her to smile or to laugh or nothing.
Combination chemotherapy is very hard on children. But I'll tell you something. I've talked to an awful lot of family, and those families have one thing in their mind. Give me back my child. If you have to hurt him to do it, that's okay. We'll live with that. In the early 60s, one had to tell parents that you only had about a 10 or 20% chance of pulling this off. And now we're at 85 or 90%. The fellows whom we're training now weep if they lose one. Whereas when I started, there was no hope for anybody.
The determination of Sidney Farber and his colleagues to beat this terrible disease was the opening shot in the war against cancer. But this enemy within proved to be a real puzzle. Combination therapy, giving highly toxic drugs all at once, seemed to be the way forward. Surely it was just a question of finding the right combination. But these early breakthroughs gave no clue as to the size of the puzzle they were facing. So, in 1962, cancer was an enigma. It was known that it involved cells that were out of control, endlessly multiplying, and then, even more sinister, infiltrating other sites in the body. As to its cause, well, there were many theories. In the UK in the 1950s, a young doctor called Richard Doll had controversially suggested some cancers might be caused by smoking. But in the 60s, 4 out of 5 men smoked. How could something so everyday cause cancer? Doll's ideas were dismissed. The big idea in science in the 60s was that cancers were caused by viruses, but it was believed that they could be cured with combinations of drugs. And that's when cancer got political. In 1964, Sidney Farber came here to Washington to testify before Congress. He brought with him photos of those few precious survivors and tried to persuade Congress that if only there was more money, cancer could be cured, not just leukemias, but all of them with combination chemotherapy. Now, they used to say of Sidney Farber that if you gave him a tambourine, he'd beat it. But even he needed bigger guns. And that's where Mary Lasker came in. Lasker was a rich socialite in her 60s whose husband worked in advertising. Ironically, his wealth came from the Lucky Strike cigarette account. With Farber, she began to use modern advertising and PR techniques to wage war on cancer. Together with her powerful friends, she lobbied ceaselessly. 1969 saw the first moon landing.
It's one small step for man.
Surely, Lasker and her rich, well-connected friends argued, if you could get a man to the moon, you could crack cancer.
One giant leap for mankind.
It was perfect timing. President Nixon was seeking re-election and was anxious for a cause to deflect public opinion from the war in Vietnam.
We find that more people each year die of cancer in the United States than all the Americans who lost their lives in World War II.
So he gave his support to the Conquest of Cancer Act. And he declared cancer would be cured in time for the American bicentennial, then just 5 years away.
The Congress is totally committed to provide the funds that are necessary, whatever is necessary, for the conquest of cancer.
Nearly $2 billion was poured into what quickly became known as the War on Cancer, funding research and creating an independent cancer agency, a NASA for cancer.
We had a philosophy that I remember from when I started back in the early 70s at the National Cancer Institute, that if we could find the right drugs, give them in the right doses, and sometimes in really high doses, we would be able to cure the disease.
During the 70s, the worlds of doctors and scientific researchers seemed to be running along parallel tracks. Doctors felt certain the future was drug combinations, whilst researchers like Bob Weinberg thought it lay in better understanding of the inner machinery of the cancer cell. And chemicals, including tobacco, were now firmly in the spotlight.
By the 1970s, there was the chemical theory on the one hand, there was the virus theory of cancer on the other hand, and also there was the theory that there were damaged genes inside cancer cells.
By the 80s, what had happened that developed the understanding of cancer?
A major step forward was made in studying viruses, ironically, that was undertaken by Michael Bishop and Harold Varmus in San Francisco, when they discovered that within the repertoire of normal genes in a normal cell, there actually lay some genes that could trigger cancer in the cell around it. What was discovered in the mid-1980s was that there really were two major kinds of cancer genes. Those that drive the unrelenting growth, multiplication of cancer cells, the so-called oncogenes, and a second class of genes whose normal function it is to damp down, to suppress cell proliferation. And this second class of genes was called tumor suppressor genes. And we came to realize, in fact, that the average cancer cell that one finds in a human has both a stuck accelerator pedal, an oncogene, and multiple defective braking mechanisms, that is, defective tumor suppressor genes.
It was Bob Weinberg's team that discovered the first oncogene. The problem was that neither doctors nor researchers were coming up with what patients needed: cures. Yes, there was new understanding, and there were some new drugs, for instance carboplatins, still in use today, but no actual cures. The 1980s were wilderness years for cancer patients, and there was growing discontent that the war on cancer had failed to deliver. Then, in 1986, came devastating criticism from a man called John Baylor. He was a public health academic from Harvard University. And I want to read what he said, which was published in the New England Journal of Medicine. "We are losing the war against cancer, notwithstanding progress against several uncommon forms of the disease. Some 35 years of intense effort, focused largely on improving treatment, must be judged a qualified failure." Well, why had it gone so wrong? Well, the answer is simple. They had misjudged their foe.
There's nothing smarter than a cancer cell. If you attack it on one side, it will escape on the other.
The fact is, from my perspective, and the terms that I use is a wily foe. It has always stayed one step ahead of us.
Not only were there no new cures, but more and more people seem to be getting cancer. Nixon's war on cancer failed to deliver immediate results, but it did prove one thing. Without political will and the ear of policymakers, a problem on this scale just can't be solved. Families like Lynn's experience with bowel cancer today reflects the past, present and future of cancer. Lynn's son Matthew was just 19 when he was diagnosed with bowel cancer.
In June 2005, Matthew first became ill. He'd got a lot of pain on his left-hand side. Over the next few months, he lost more and more weight until he'd lost in total 3 stone. He had blood tests, he was very anaemic, and he was sent for a colonoscopy, and that's when he was diagnosed.
Tell me about Matthew's treatment.
He had the whole of his colon and his spleen removed, and then he had 25 sessions of radiotherapy, followed by 9 months of chemotherapy.
So, modern treatment combines chemotherapy and radiotherapy and surgery. Matthew now leads a normal life, but if he'd had his operation 50 years ago, it would have been a very different story. Until recently, the concept of radical surgery, pioneered by American surgeon William Halsted, ruled. He thought that if a patient's cancer returned, it was only because the operation hadn't been aggressive enough. For breast cancer, women routinely had both breasts removed, chest and arm muscles, even ribs, causing gross disfigurement and often lifelong pain and disability. I've come to Italy, to the European Institute of Oncology, to meet Professor Umberto Veronesi. As a young doctor in the 60s, he believed that there must be a better way to treat cancer. Soon, he was to radically challenge established wisdom.
I realized that the mastectomy was not always necessary. You can imagine I was considered a quack, a charlatan.
Dr. Veronesi did not win a popularity contest with that idea because the surgeons were convinced that Halsted was right. Now, there were younger surgeons who knew that Veronesi was right. In fact, in the 70s, when all this was beginning to occur, it was the younger surgeons who were cheering because they had become quite suspicious.
Medicine and surgery is a business. And many surgeons understood that abandoning mastectomy would mean for them much less income. But I am a very stubborn man. And I decided to organize a trial, a randomized trial, comparing women having the mastectomy with the women having the conservative surgery. And the results after 10 years was the same, no difference. This was a fantastic day when I look at the data. Finally, I showed to all the surgical world that I was right.
The influence of Veronesi and other pioneers of less invasive surgery has been profound in all cancers. This patient is having their bowel tumour removed using keyhole surgery. It involves a small cut, whereas bowel cancer surgery 20 years ago would have meant a chest to pubic bone incision. And it's not the only change.
I qualified in 1984, and surgery was a very, very different thing in those days. Surgery isn't just what happens in an operating theatre. Surgery is about prior to the surgery and how you make your diagnosis, how do you plan the operation, and that has been dramatically changed. I mean, in those days, if we made the diagnosis of cancer based on a piece of tissue, we had really no way of staging that cancer. In other words, to see whether it's confined to the area, whether it's spread anywhere else. And, you know, most patients were in hospital for about 2 weeks. We had patients on starving for about 5 days before we gave them anything to drink or eat. They were up on a drip. And then the aftercare was also very, very different. So a lot has happened since I've qualified.
But one thing has stayed the same. In the 1960s, surgery cured more people than any other treatment. And the same is true today. But surgery's many advances and refinements over the last 50 years mean that today it's not only more effective, but kinder and gentler too. the 1960s and 70s, even diagnosing cancer was difficult.
All we had really were plain x-rays. I can remember consenting patients for procedures which had the title of exploratory laparotomy, but what it really meant was the surgeon just had to take the patient to theatre, open up the abdomen, have a look inside, and quite often the answer was there was nothing they could do.
If you had a cancer in your body, then surgery might reveal it. But if you had a cancer deep inside your skull, then surgery wasn't an option. How to see inside the skull was a problem that occupied a man called Godfrey Hounsfield. In 1967, Godfrey was walking through this gorgeous Nottinghamshire countryside when he came up with an idea, and it was this. Imagine that you have an object inside a box. How can you tell what that object is using X-ray? Well, if you use a single X-ray beam, you wouldn't be able to tell what it was. But if you were to use multiple X-ray beams, essentially you would be able to see the object inside from every angle. And if, as the beams passed through, they were analysed by a computer, you would be able to build up an image of the object inside. It was the beginning of computerised tomography, what we know better as CT scanning. The first CT scanner was put into operation in 1975. It revolutionised medicine and, in particular, the diagnosis and treatment of cancer.
With, as we call tomography, with 3D imaging, you could actually precisely define the anatomy of the normal tissue and the tissue being involved by the disease process. It completely changed the investigation of cancer.
And then came magnetic resonance imaging, MRI, invented by Peter Mansfield. It uses strong magnets rather than X-rays and is especially useful for looking at the soft tissues of the brain and muscles. And there was another way of revealing cancer, nuclear medicine. Back in the early 60s, some patients got medicines containing tiny doses of specially designed radioactive probes, which found their way to particular tissues.
I'm making the injection now. Flush now, please.
The probes then showed up as glowing hotspots on camera images. Nuclear medicine can show not just if cancers are there, but how they're working. A further development called PET, positron emission tomography, widened its applications, but then came a dramatic advance.
The step change was to marry a PET scanner onto a CT scanner, and therefore combine the fantastic anatomical detail and resolution of a CT scan with the exact distribution of the radiolabeled probe to be used in a particular patient. So suddenly we could make major inroads in the assessment of disease response. So instead of waiting 3 months after some chemotherapeutic regime to understand whether the patient is responding, we can now offer response in days, few days, 1 week, and therefore guide a new assessment as to whether one should persist with that particular disease regime or whether one should change.
In 50 years, cancer has gone from being hidden from us to being revealed. And imaging has been the ultimate enabler, allowing earlier diagnosis and more accurate surgery. Imaging was critical to another area of cancer treatment, one that had been around for over a century, the use of radiation.
Radiation has been used in cancer because when you deliver a given dose to cells, you destroy them. Unfortunately, there is a difficulty with ionizing radiation is that it does not make the difference between a cancer cell on one side and a normal cell on the other side. So all the difficulty for us, or the trick or the challenge, is to be able to really focus the dose to the cancer cells, avoiding the surrounding normal tissues.
The development of LINACs, linear accelerators, meant X-rays could penetrate deeper into the body. But there was still collateral damage, which limited the use of radiotherapy, particularly where tumours were in awkward places or were of odd sizes.
I guess the next big quantum leap started in the mid-1990s in some research centers with the development of what we call today IMRT, which stands for Intensity Modulated Radiation Therapy, which means that if we have a target volume which is this shape, the radiation will have this shape too.
IMRT now made it possible to flood an entire tumour with radiation. Further refinements of IMRT have arrived in the last 15 years. The latest generation are stereotactic machines. They deliver a precision exocet of radiation using many narrow beams to pinpoint an exact part of a tumour.
In normal radiotherapy, we account for breathing motion by treating a region within which the tumour will move up and down. Because the CyberKnife can track the breathing motion, we can just treat the tumour itself, and while the tumour is moving up and down with the breathing cycle, the machine will move up and down with the target in that point of space. It has two main components to it. It's this part here, which is a linear accelerator, and this is attached to a very sophisticated six-jointed robot. This robot is the same sort of robot that's used in motor manufacturing, and is so well engineered it can move anything to a point in space to an accuracy of less than a millimetre.
Advances in radiotherapy have mainly come from developments outside medicine, like robotics and more powerful computing. And the introduction of imaging has transformed the success of radiotherapy. It remains the second most important form of treatment after surgery. With Matthew on the road to recovery, you might have thought it would be the end of his family's ordeal with bowel cancer. But what happened next was extraordinary.
I was diagnosed with colon cancer. We were told then that, you know, it would definitely be genetic and they needed to look at family history then. I was aware that my father died in his early 40s.
The hospital were anxious that Lynn should get in touch with her father's family, but there was a problem.
Apparently the marriage split up before I was a year old and I never had contact with him. My daughter and myself decided to do a sponsored walk to raise funds for the new cancer centre that was opening in Nottingham. And the reporter there was talking to people that were doing the walk. She was interested in mine and Matthew's story. And during the course of talking to her, it came out that I didn't know my family. And she suggested doing an article on Matthew's story. The following morning, the reporter rang me and said, you know, your half-sister's been in touch and are you ready for this? You've got two half-sisters and a half-brother and a stepmother who were all very interested in meeting you.
What she discovered next was the darkest of pictures.
My grandma on my dad's side had had bowel cancer. Her sister had had it, and my dad's sister had also had it, and she'd lost her son with it at the age of 38.
Understanding what was behind those families with many cases of cancer they led us to identify the genes that were responsible.
For some cancer families, the significance of the tumour suppressor genes discovered by Weinberg in the 1980s had become clear.
One now realizes that in many cancer susceptibility syndromes in which there's a familial pattern of developing one or another kind of cancer, that pattern is caused by the inheritance of a defective tumour suppressor gene from one's parents.
We now understand that cancer is also the result of multiple random gene faults in cells, accumulated over a lifetime, caused by external factors like the chemicals in tobacco smoke or by radiation, for instance, but also by normal chemical reactions, providing energy inside our cells.
Scientists like myself like simple solutions rather than extremely complex ones, but ultimately we have to bend to the winds of reality. Cancer is a very complex disease.
Knowledge of the genetics and molecular biology of cancer is a phenomenon that only really began in the 1970s. But genetics is now the foundation of our understanding of cancer and how to defeat it. And then the first treatment to emerge from this new knowledge of molecular biology and genetics came. And once again, as so often in the history of cancer, it was from leukemia, and in particular, a type known as chronic myeloid leukemia.
I was working in a lab on the regulation of cell growth, what causes cells to grow or what causes them to disobey normal growth signals. And one of the key regulators of growth is a family of enzymes called kinases. And I was also trained as a medical oncologist, meaning I took care of cancer patients. As I looked at the field, or surveyed the field, where was there a kinase, one of these growth-regulating enzymes that caused cancer? And it was clear to me that one disease called chronic myeloid leukemia, or CML, was a disease that was absolutely clearly caused by excess activity of one of these kinases. And so I began to move all my lab work into this one particular disease, CML, to identify compounds that could shut down these enzymes that were unregulated in this disease. And I figured that I'd go into the lab, I'd probably disappear, and that maybe someday I might make a contribution in this new way of thinking about cancer. I really never dreamed that I'd actually bring a drug out of the lab into the clinic. For me, it was just, I wanted to do something that was different than chemotherapy approach.
I still remember, as if I was there today, the moment when Brian Drucker reported his remarkable initial results with Gleevec. Quite remarkable clinical responses in patients who were otherwise destined to die. And you could really see this as a future model for how we were going to treat so many of our other patients with leukemia.
I was 24 years old when I was first diagnosed. I had a bone marrow transplant 6 months after that, which basically worked for 4 years, and then the leukemia came back. I've been on various drugs regimes. Quality of life, it was never great for 15 years before I got to taking Gleevec.
We talked to Julian Tutty, who has CML. What would you say if you met Brian Drucker?
I'd probably be speechless, to be honest.
I'd just give him a hug and say, thank you so much.
That man saved my life.
Thank you. You know, it's just so amazing to think about the numbers of people whose lives have been affected.
Then came the use of monoclonal antibodies, essentially chemical sniffer dogs designed to seek out particular features of cancer cells and disrupt them. Their early use wasn't promising, but later versions of monoclonal antibodies had an extraordinary effect, particularly in the treatment of other leukemias and some forms of breast cancer. So Gleevec set the cancer world on fire, and other drugs followed, notably Herceptin for breast cancer. Targeted therapies provided new hope, because if you could find the mechanism behind a particular cancer and then target it with a drug, then surely every cancer could be conquered.
When Doug Hanahan and I walked down into the mouth of the volcano in Hawaii, we thought that there must be a way to describe the entire complex phenomena of human cancer and all the various kinds of diseases in terms of a small number of unifying principles: sustaining proliferation, evading growth suppressive signals, resisting cell death, proliferating indefinitely, and invading and metastasizing. One of the critical aberrant traits of cancer cells is the process that is termed angiogenesis, in which a tumor growing within a tissue begins to recruit blood vessels to grow into the tissue, because the tumor cells, like normal cells, require a blood supply.
In the mid-90s, the oncology world was buzzing. A researcher here at Genentech in San Francisco had discovered VEGF, which enables tumours to help themselves to a blood supply.
I felt extremely fortunate, that I came across VEGF as being because there was lots of people were searching for this tumor angiogenesis factor, a valid, target, because blocking angiogenesis could be a real strategy to treat, cancer.
This seemed to be a highly selective silver bullet for killing the tumors without damaging adjacent tissue. The fact is, a decade later, we came to realize that many of the anti-angiogenesis therapies that were designed to prevent the ingrowth of vessels into tumors didn't work that well. And they didn't work that well for a variety of reasons, in no small part because tumor cells were clever enough to figure alternative ways to circumvent the therapies thrown against them that were designed to starve them of new blood vessels.
Drugs that starve tumours of their blood supply are important, especially in bowel cancer. But they've proved not to be the single answer. They have, however, highlighted the critical importance of the tumour's immediate surroundings, its microenvironment, to its growth.
50 years ago, we would think of cancer just as a ball of malignant cells, the cells gone wrong. Now we know that any cancer mass is in fact a complex microenvironment, a rogue organ in which many normal, usually good cells of the body are recruited and corrupted by the cancer cells to help it grow and spread.
And this understanding that cancer is a rogue organ rather than simply a group of defective cells goes some way to explain why it's so hard to beat. But for all the progress we've made, curing some and turning others into chronic diseases, there are still too many types, like pancreatic cancer, for which the outcome is as bleak today as it was 50 years ago.
I've been feeling tired, just tired, but more and more tired, until it got to the point where I thought maybe there was something amiss. So I went to the doctor. He'd referred me to a consultant. And then they were able to tell me very quickly what actually it was. And we were just stunned, really, just...
The challenge for those with pancreatic cancer is that it's often well advanced at the point of diagnosis, when there are no longer any effective treatments. However, Bobby was able to take part in a clinical trial. These are invaluable to researchers in developing new treatments, and it gave her some hope of a return to normal life.
I just want to be around with my family, my husband. I want to be there to... I just want to be there to look after them. And I'm just not ready to go yet. I've got so many things I want to do.
People like Bobby and countless others in the past 50 years are the real heroes of cancer research. Without patients willing to participate in trials, research would be almost impossible.
I think patients, like health professionals, recognise that it's only through research are we going to make progress. And for a disease as devastating as pancreatic cancer, we really need a breakthrough. And that's only going to come by exploring new forms of therapy in the context of a clinical trial.
Clinical trials have established the effectiveness of some of the most important therapies and treatments we have. For instance, the trials of tamoxifen, which blocks a hormone essential to the development of breast cancer. It's what's called an adjuvant treatment.
For some subsets of breast cancer, the risk of relapse is going to be 50%. That means that following surgery, 50% of the patient, at least, have remaining cells, which you cannot see. So the idea was, can we apply chemotherapy in those patients with remaining tumor cells that we cannot see in order to prevent relapse and, if possible, to increase the cure rate?
Adjuvants given after surgery or radiotherapy and neoadjuvants, which are given before, are now extremely important. And these sort of drugs may be key in the future for prevention.
There are already trials ongoing using hormone-altering agents like tamoxifen and other agents in patients who are at risk of breast cancer, either because they've already had the disease or because they have a genetic risk of it.
Collaboration across borders has long been required for trials of rarer types of cancer.
Doing studies in more than one culture, one community, gives us the opportunity to reach a much larger number of patients in a short space of time, particularly for rare forms of cancer. And although pancreatic cancer kills a large number of people, actually it's relatively uncommon in its instance. We actually need to go further than the UK to get the numbers up in the time frame that's meaningful.
And as more subsets of common cancers are identified, each one is becoming a rare cancer.
To validly compare two treatments, you have to accrue significant number of patients to have sound statistics. And because now we know so much the molecular characteristic of cancer, we have to compare not apples and pears, but really patients with the same molecular characteristics. So you need the same type of patient. And that is becoming extremely difficult.
The extra months Bobby's trial gave her came to an end all too soon. Within a few short weeks of meeting her, like so many before her, she died of this dreadful disease. Clinical trials like the one Bobby was involved in help clinicians and scientists make another small step in their understanding of treatments. Clinical trials are often very complex by design, but they're the only way to prove whether something works. And without them and the courage of patients like Bobby, very little progress would have been made. Throughout the fight with cancer, doctors have had to confront situations where they have no more treatment options. Palliative care for the dying was an alien concept to many physicians. Today, hospices like this are an integral part of cancer care, but 30 years ago, hospices hardly existed. The hospice movement was spearheaded by a remarkable woman, Dame Cicely Saunders.
Cicely was a driving force, a very impressive person. She was tall, she had presence, she had enthusiasm, if you like, she had charisma. Because of Cicely's influence, the whole movement towards good palliative care moved with amazing speed.
I was literally exhausted when I came in, physically and mentally probably. And so I don't know, it's given me peace of mind.
We're more than physical, and this was a point that Cicely made right from the beginning, that there are, if you like, 4 dimensions to our personhood. There's the physical, yes, the psychological, the social, and the spiritual, and all these areas have to be addressed.
For me, they've relieved any fear that I may have had about the process of cancer and dying. And if you can end your days without that fear of suffering, what is there to worry about?
Yes, we continue to look after the physical needs. Yes, we are giving drugs to control this pain and that symptom. But unless we do it within this holistic context, then we're going to let our patients down and patients will continue to suffer.
Acknowledging the importance of caring for those for whom no further treatment options are possible was difficult for the medical establishment to come to terms with. It's now accepted that palliative care has to be part of what's available to cancer patients, although it continues to be largely funded through charitable giving. Over the years, the death of a mother, father, son, daughter or friend has motivated people into action.
All over the world, millions of people take part in fundraising events like this one to raise money for cancer research.
Who are you all doing it for?
Sylvia!
But this fundraising phenomenon isn't a new thing, as this advert from the 1960s shows.
Those who understand the urgency of the work. The campaign cannot prevail without
The first really effective fundraising can probably be traced back to Mary Lasker and Sidney Farber in the US in the 1970s. Now, billions are raised every year through charitable giving.
1,
The massive engagement of patients, their families and the public with organisations such as Cancer Research UK has made a huge difference not only to basic cancer research, which has to be funded on a large scale in order to have the appropriate scope and ambition, but also to the organisation of cancer treatments. And that's a phenomenon which is spreading out all over the world, really.
But there is a perhaps inevitable disparity in fundraising across cancer types. Awareness of some, particularly breast cancer, has been raised thanks to high-profile patients like Betty Ford and Kylie Minogue. And better outcomes motivates further fundraising. But in cancers where fewer survive and there is less awareness and relatively little fundraising, progress is much slower. As cancer emerged from the hushed tones and shadows of the 1960s, so people became motivated to act, and their voices became louder and louder, even more so with the advent of the internet and then social media. Whether it was taking part in trials, being involved in advocacy, or simply being one of the millions raising money for research, people power has become an incredibly important weapon in the fight against cancer. The discoveries that genes were involved in the mechanisms of cancer were incredibly exciting, but it was very slow and laborious work. Working out whether a family member carries an altered gene used to take years. Today, it can take as little as 40 minutes using a gene sequencing machine like this. This room surely deserves a place in cancer history, because it was here in the Sanger Institute in Cambridge that the majority of the work decoding the human genome took place. The entire sequence was announced in 2001. And gene sequencing is surely the future in understanding cancer and how it works. The Human Genome Project heralded a new dawn for cancer in the 21st century. Thanks to high-speed sequencing, it was now possible to examine the inner mechanisms of cancer cells. And what they found was shocking.
Now that we have experience of sequencing tens, even hundreds of whole cancer genomes, we can see laid out before us that actually everybody's cancer is different from everybody else's cancer. Each cancer may have something like 5,000 to 100,000 mutations, and these are distributed across the genome. And it's turning out that no two cancers are the same.
So what does this all mean for treatment? Well, rather than focusing on where a cancer is in the body, you treat each tumour as an individual, finding out what's driving its growth and developing therapies which combat it. It's an approach called personalised medicine, and there's a very good example of that in the new treatments now emerging for melanoma. This skin cancer is on the rise due to increased exposure to the sun, and there have been few treatments available for it.
When you are told you have melanoma, then it's just, terror, because it's deadly and it goes very fast.
The outlook for this young woman looked bleak, but a glimmer of hope had emerged, thanks to research carried out by Richard Marray. Genetic research at the Sanger Institute had established that a protein called BRAF was found much more commonly in some melanomas.
BRAF is a protein that controls how cells communicate with each other, and its normal function is to tell cells where they are. We have 13 billion cells in our body, and they need to be coordinated, and one of the proteins that tells cells where they are and what they should do is BRAF. And so we manipulated the BRAF protein in cells. We either took it away or added it back in cells, and what we found when we did that was that we could make melanocytes, which are the precursors of melanoma, the cells that melanoma develops out of. By manipulating BRAF, we could turn their growth on and off. And that told us that the mutations actually had a biological property and made the tumor cells grow.
When we realized that there were some lymph nodes that were taken, we had surgery, and that was confirmation that the disease was progressing. You're operating in this constant fear and uncertainty, and it's the first thing you wake up, that's what you think about. It's the last thing, you know, the last thought on your mind. And it's hard also to deal with others because everybody else wants you just to get over it.
Having established the significance of BRAF, a number of drugs have been developed that target it. One of them is called Zelboraf. It has the potential to inhibit tumour cell growth, but only in those patients whose melanoma carries that BRAF mutation.
In order to be able to decide what drug to give to a patient, you need to have a companion diagnostic. And what I mean by that is you need to be able to determine whether they have the feature that will make them sensitive to the drug, and then you need to be able to do that in real time so that the clinician can decide within a few days what treatment to give the patient.
I knew I carried the mutation. And you just kind of like think, wow, miracle, you know, you're going to be the lucky one to get the drug at the right time. The disease just like disappears. And when you have your first set of scans, it's just like exhilarating. Unfortunately, the tumor that had been resected grew again. But I look back and I think, yeah, Zelboraf gave me 7, 8, 9 months of okay life.
So it turns out that tumour cells are very adaptive, and when you put a selective pressure on them, in very much the same way that organisms can adapt in an evolutionary sense to new environments, tumour cells adapt to the new environment, and the new environment is the presence of the drug. And so they evolve very much in the way Darwin described for species evolution, to become resistant to the drug. They learn to get around it. And so what we obviously need to do is to try and work out how to make the drugs work better, but more importantly, for a much longer time.
There is optimism because it's clear that there is not an infinite number of ways that a cancer can get around a new treatment. It may only have 2 or 3 ways of finding its way around. And if we can find ways of blocking all 2 or 3, then we may win the battle against that type of cancer.
Clearly there are enormous opportunities for personalised medicine because we can start to tailor treatment to individual patients. And what we hope is that eventually we'll have really a panel of drugs that we can draw from and that we can mix up in very clever combinations for specific patients and to improve their treatment.
In a way, Sidney Farber was right. A combination approach to cancer therapy has a good chance of working better than a single agent. But cancer is a lot more complicated than he realised 50 years ago.
The cutting edge of cancer treatments is personalised medicines. These promise to help deliver not only new medicines, but also using what are called companion diagnostics, tests to identify which people will benefit most from them. One of the greatest challenges we face is trying to deal with metastatic cancer. That's cancer that's spread beyond its primary source. It's very hard to treat, and it's the cause of most cancer deaths. So while scientists try to figure out why it happens, how about trying to prevent it happening altogether? You can go for earlier diagnosis, or better still, preventing it altogether. And there's no better example of that than smoking.
Back in the 1960s, smoking wasn't just normal, it was something which you aspired to.
Over 80% of men in the United Kingdom smoked. And then we came along with this remarkable findings from Richard Doll, essentially, and then other people followed it up, and we all came to the same result.
First of all, they discovered the link with lung cancer. They hadn't at that stage discovered the link with heart disease. Then that was discovered, and so the news kept coming out and getting worse and worse for smoking. Clearly, the tobacco companies saw a threat to their business. So they got the lawyers in to try to mislead the public and politicians and the medical community for the last 50 years.
People born before 1900, 60% of them died of cancer, and that's now reduced to about 27 to 30%. The most important factor is smoking. Smoking is very strongly associated with about 20 different forms of cancer: lung cancer, pancreas, head and neck, esophagus, etc. So it's a real major contributor to the big changes which have taken place in the incidence of mortality from cancer over the last 100 years.
But these changes in the West don't represent global trends. In China, over half of all men smoke, and although only 2.5% of women smoke, fears are that this will rise.
Even if they get the rates down in men, Westernization of that country is probably going to be the single most important public health threat that they face as the smoking prevalence in women goes up, which it will do from 2.5%, even if it only went up to 10 or 15%. You know, there's a lot of people in China. You're talking about a huge number of deaths.
And it's not just smoking. Work done by epidemiologists has identified other significant causes of cancer.
The other factor which we've clarified is alcohol. Alcohol drinking is a risk factor for cancer of the head and neck, the esophagus, one or two other things. We've also clarified the role of sunlight in the cause of skin cancer, and particularly in melanoma. And we've moved recently, the big recent development has been in understanding the role of sunbeds, which are very, very dangerous, particularly in younger users. We did this report in France to work out the attributable causes of cancer in France, and 10% of breast cancer in France in 2000 could be attributed to HRT use. All of that's come from observational studies, epidemiological studies. None of it's come from a randomised trial.
But although decades of research have proved that these external factors play an important role in causing cancer, and scientists have pinned down a number of hereditary gene faults, for many, the cause of their cancer remains a mystery. Back in the 1960s, people believed cancer only had one cause, and top of the suspect list were viruses. We now know that a few cancers are indeed caused by viruses. Human papillomavirus causes cervical cancer. Hepatitis B, some forms of liver cancer. The development of vaccines to counteract these viral infections has been one of the major achievements in prevention over the last 2 decades. The introduction of mammography and cervical screening came after decades of effort by clinicians across the globe to prove their effectiveness. Increasing public awareness of the signs and symptoms is also very important for earlier detection. And for families like Lynn's, it's now possible for them to be screened for HNPCC, the inherited genetic variation now known to make them susceptible to bowel cancer.
I was told that what they thought from tests on my tumour was that we had HNPCC. The news that it wasn't just Matthew affected, that it was my daughter Alison and my eldest son Robert. I think I feel a lot of guilt that I've passed it on to them. But I'm relieved that there's screening, which should prevent it ever growing into a full-blown cancer.
Screening has had a major impact on some cancers, and population studies by epidemiologists have helped to identify causes like sun exposure, infection, and of course, smoking. It's enabled large-scale preventive measures to be put in place, particularly in the West. Prevention is better and cheaper than cure. But there are many challenges: an ageing population, continuing rise in cancer deaths from smoking in Africa and in China, and right across the globe, tackling the risk factors associated with alcohol and obesity are proving extraordinarily difficult. And where's the next battlefield going to be in the fight against cancer? Well, history has a funny way of repeating itself. Monoclonal antibodies were dismissed in the 80s but came back triumphantly in the 90s in drugs like Herceptin to treat breast cancer. And what about the immune system? Well, that too was dismissed as a way of fighting cancer, but now it looks as though immunotherapy may be the treatment of the future.
We think that probably bodies generate tiny cancers all the time, but that these get mopped up by the body's immunity because they're visible to the immune system. So when you've developed a cancer, when it's become apparent, what we think has happened is that that's evaded the detection of the immune system. It somehow got under the radar and managed to grow despite the immune system being there. And a lot of the progress we've made in the last few years has been about working out how you turn that back on, how you make the cells visible again, and how you uninhibit the immune system to allow it to do the work it should be doing. More recently, we've started to see more sophisticated approaches to changing the regulation of the immune system, either by switching off some of the stop signals, which would normally control it with antibodies, and also by producing populations of cells which are specifically geared to target things that you find on the tumour cell surface. So we're getting progressively more sophisticated.
Immunotherapy looks very promising, but everywhere there are dazzling new prospects for the future.
The intelligent knife is a completely new concept, and that is, could we, for example, during an operation, obtain bits of tissue to give us an immediate diagnosis of what we're looking at? Is it cancer? Is it not? If it's not a cancer, is it about to become cancer?
In radiotherapy, the future will be about personalised doses based on the type of tumour being targeted.
Some patients may need more dose. Some may need less dose. Why? Because we have seen that they have a particular molecular factor that make them or that make the tumour a little bit more sensitive to ionizing radiation.
Better imaging will deliver ever more detailed and accurate pictures of tumours.
But we want to investigate other properties of the tumour, such, for example, as the ability of the tumour to respond to oxygen treatment. And by doing these different types of investigations, we are really producing a new map of information, of different signals of a particular tumour.
And genetic research will deliver more detailed and comprehensive information about the makeup of cancer.
In recent years, we've been empowered by these extraordinary changes in DNA sequencing technology, which means we can now sequence the complete cancer genome and hundreds and thousands of complete cancer genomes, finding all the mutations within them. That is going to give us a completely new set of targets for the development of drugs. So development of cancer therapeutics is going to be hugely empowered by all this knowledge.
We tend to think of advances only in terms of new treatments, but actually the reorganisation of cancer services within hospitals has had a profound impact. This has had to be implemented because now cancer is subjected not to one drug or one treatment, but to different combinations of treatments and technologies. It's meant cancer is most successfully delivered by multidisciplinary teams.
It's no good at all unless we get the services organised so that patients get diagnosed early, so that they get assessed by which of these treatments is going to be best for the individual patient, and so that they then get into having the right treatment.
When I first started practicing, I made all the decisions. I cannot make those decisions now. I have to make those decisions in partnership with experts in the drugs, which are the oncologists, experts in the X-ray treatment, we would call radiotherapy, clinical oncologist, experts in the radiologist who essentially look at these images, because they help me plan the operation. So I don't go in and say, as we did 20 years ago, find the unexpected.
The organisation of cancer services isn't a piece of the puzzle in itself, but it's the glue that holds everything together. And it's not just about doctors, nurses or hospitals, it's part of a much bigger picture. Cancer is as political now as it was in the 60s or 70s. Today, the issues across Europe are mainly about access and cost, issues that may become even more challenging with the advent of personalised medicines, which promise cure for a few, but which come with a high price tag. These are not issues that politicians can decide. These are issues for the whole of society. It must decide what it values.
What's the point to develop very effective treatment if no healthcare providers or no government can support them? So this is another dimension, another challenge for healthcare providers and social securities, is who is going to be able to afford the treatment that we are currently developing?
Well, I think as society we want to afford good cancer care and good cancer treatment. Yes, there are going to be very big challenges there. There is potential for it to become more and more expensive. But what we really need to look at is where we can use the resources we've got to maximum benefit. By preventing cancer, obviously that means that we're not going to spend the money on having to treat patients. Early diagnosis may mean that we don't have to give the expensive drugs further down the track. Targeting the expensive drugs are the people who are really going to benefit from them.
So if we can get that right and say, we know this drug is the drug that actually matches your cancer, we also know what dose we're going to use to treat your cancer, that will have a huge impact on our current expenditure in cancer, because it will be a much more intelligent way of spending our money in cancer.
Today, cancer is part of our life. It's part of our political agenda. It's part of the agenda where in a time of very limited resources, we have to fight in order to get more research dollars for cancer, or at least maintain research dollars for cancer so we don't lose ground.
When an emergency arises, governments can find money to cope with it. I think we've got to get across that cancer at the present time, globally, is a public health emergency.
Back in Sweden, Kate's family represents the modern face of cancer.
Well, Kate finished her treatments after 2 years, and now she's an 11-year-old, very happy girl, full of life, who is an inspiration to other kids going through treatment, so they can see that there is life once it's done, that you can get through it. Why don't you follow me and we'll go see Kate?
Lovely.
Hi, hi.
Hello, Trouble. What would you say to any children now who had leukemia like you?
Keep on taking the medicine and don't skip it. And survive.
And they'll be as healthy as you are.
Yeah.
It's taken 50 years to turn leukemia into a disease survived by 95% of children. We can see that discovery can take 2 decades or more to translate into new treatments, and that sometimes advance depends on the development of other technologies, like the ability to rapidly sequence genes or powerful computing.
Will children still get leukemia in the future? Sadly, yes. But far more of them will survive it. And it's living with cancer or after cancer that's going to be one of the greatest challenges for the future.
Obviously, one of the big challenges is that as we are more successful, more people are alive, but more people are alive potentially suffering from the consequences of cancer treatments. So, first of all, we need to make sure we do minimise those consequences from the outset by targeting the radiotherapy more precisely, for example. But also on top of that, we need to make sure that the support is there for people in the long term. We know that a lot of people get back to a normal life, but some do not, and we need to be able to support them better. So that's a big challenge for the future.
So there's another piece to add. Survivorship. Learning how to live with cancer. We now know that cancer is as individual as we are, and that there never will be a single cure. But we do have cures for some, and others we're learning to live with. Above all, we know that collaboration across disciplines and across borders is our best hope of defeating cancer. This puzzle isn't complete. Perhaps it never will be. But we know that with every new step, every new glimmer of hope, we come closer to defeating our enemy within.